Hey folks, okay, last time we looked at dynamically allocating and deallocating arrays and our use of pointers and new and delete, and we mentioned the idea of dynamic data structures, but we didn't get into it much. So today we're going to try building some. So what this is going to involve is allocating and deallocating single items and creating a way to have so that one item can have data in it and it can also have pointers to other items. That way we can kind of connect items together. So that's what we're going to take a look at. We'll use structs for this for now. A little later on in the course we'll get into talking about classes in a pretty similar way, but for now we'll play with dynamically allocating and deallocating structs and gluing the beasties together. Alright, so again, the notion is that the structs will have some data fields in them, and they'll also have pointers to other structs, so that we can have a pointer to the next one in line or to a couple of others that are related to the current one. And then we can use new and delete to go through and dynamically create a new item and then set the pointer in one of them to point to the other one, so that we can start chaining these things together to build up a data structure over time. And when we need to, we can do the reverse, is take an item, delete it, and set the pointer to it to null so that nothing's referring to it anymore. So again, this allows us to create all sorts of different data structures, lists and trees and graphs that incrementally grow and shrink over time. We add one more item to the tree or the list or the graph, or we pull one out and delete it. So what I'm going to do is start with the syntax for just creating and deleting single items. Then we'll go on to structs in particular, and there's a couple of different forms of syntax for structs. So we'll look at each of those, and then we'll get into using all of this on dynamic data structures. So that is the current plan. For allocating and deallocating just a single item instead of allocating an array of things, it's the same syntax, we just don't need to specify the size. So if I say new int, I just want one new int. If I want a new float, I just want one new float, or a new string, I just want one new string. And again, the idea is it returns a pointer to it. So I can say, oh, I'm going to have a pointer for an int, I'm going to ask for one new int, and I'm going to store the address in my pointer. Right? Same thing for a new float or a new string. And again, we've still got the issue that it's possible this won't work. Right? It's not likely that we don't have enough memory for one more int or one more float or one more string, but it could happen. So we still want to check for null, make sure that iPointer isn't null after we do this, just to make sure that it did actually work. And that gets particularly important as we start creating instances of new, more complex items that do take up more memory space. Now, again, we can still use our pointer to get at the contents. I can read a value into memory wherever the pointer says this thing exists, or I can print out the contents of memory, or I can use it in the same way as any other variable. I'm just saying, okay, well, I get at it through the pointer now, so star and whatever the pointer name is. Now, when the time comes that we're done with this newly allocated thing, we still use delete, but since it's not an array anymore, it's just delete and the pointer name. We don't have the square brackets in there that we did for arrays. So, relatively simple to move from allocating and deallocating arrays to allocating and deallocating single items. Now, this works for structs, so I can happily go through and create, if I've got a struct for a point that's got, two fields for an int and an integer x and an integer y. I can use the same sort of idea to create one, right? New point, or if I want to create an array of points, I can say new point and the size, and it's going to create an array of these things, right? It's either a pointer to so p is a pointer to just the one new item, or the array points is a pointer to essentially the first element in this array of 10 points. So I can go through and allocate these the same way as we've looked at previously, and I can delete them the same, right? If I'm deleting just a single one, it's just delete and then the name of the pointer. And if I'm deleting an array, it's delete and the square brackets and the array name. The catch comes in when we try and access one of the fields. So if I try and access the x or the y field through our pointer, we've got to be a little careful with our syntax when we do that. So we still need that asterisk to get at the struct itself, so we need our asterisk p or our asterisk array points to get at the contents of the pointer, the right location in memory. But we also need that dot to get at the specific field that we want, the dot x or the dot y. So I strongly recommend that you use asterisk and the pointer name in brackets and then the dot and field name. And that just kind of eliminates any possible ambiguity in what you're trying to get the address of. I mean, it might look obvious for this one, but as soon as we start getting into more complex hierarchies of structs, you'll see that it gets kind of ugly kind of quickly. So again, let's say I want a single new point, and so I use my star p as my pointer. I create a new point. I check and make sure that it worked, make sure that it's not null, and then I ask the user to enter the x and the y values. So again, it's the star p to get at the pointer, the right memory location, and then the dot x to get at the right field, right? The star p and then the dot y to get at the right field. So that is the kind of most fundamental core syntax, if you like, based on our asterisk to dereference and our dot to get at a field. Now, this does get a little uglier if we've got pointers to structs inside a struct that we have a pointer to. So if we start getting these kind of pointer to pointers to pointers type of thing where they're all buried in fields. So here we've got our points the same as before, right? It's a struct with an x and a y field. And then for a circle, we're going to have a struct that's got a pointer to one of these points, and it's got a radius field. So when we create a circle, we're going to have to dynamically allocate a point. We're going to have to use new point to create this thing. Now let's suppose that we dynamically allocate a circle. So we're going to have a circle that we create using new, and inside it we're going to have a point that we create using new. So here we do our circle star for a pointer to a circle. We allocate a new circle. We check and make sure that it's not null. And as long as that works, we go through and say, okay, well, I want to store a pointer in there. I want to create a pointer and store it. So I want to go through my star, whatever my circle pointer is, dot, and the point field. And then I want to create a new point and store it in that field. So far, so good. But now suppose I want to set the x and the y value inside that point. So now to get at it, I need my star c pointer dot point to get at the point itself. But that thing is itself a pointer. So to get at its x field, I need the star and then the dot. So I wind up with this, there's getting at the memory for my circle. There's specifying that I want to get at the point field in it. And there is specifying that that point field is itself a pointer, and I want to go through it to get at the x field. And then the same thing for the y. Again, the syntax starts getting kind of ugly. So we would like a cleaner syntax. And I'm going to highly recommend that you use the other syntax, this one. So as an equivalent syntax for when we're going through a pointer to get at a struct, you use a dash and a greater than symbol. So it looks kind of like an arrow. So if I use p dash greater than f instead of the star p dot f, it has the same effect. So now for that previous example, where I created a new circle and I want to set its point field. So I go through the pointer and I use the dash greater than in the field. So now it's my circle pointer, dash greater, and my point. And I set that equal to my new point. So it doesn't make a big difference. It's not that much simpler than the previous example for this part. But now, when I want to go through this pointer to get at the x field, I can simply write it like this. Go from my c pointer into the point field, and from there into the x field. So you use the dash greater thans basically to say, okay, well, follow this pointer into this field. And if you think of it that way, you can just chain these things together and you can go as deep as you like. And again, you can see that that syntax is a whole lot easier to debug than the syntax we had the first time around. Now, again, this is only for going through pointers to get at the fields of a struct. But if that's what you're doing, this is a really useful syntax. And this is going to be the syntax that I prefer for the most part. All right, so now let's get into our idea of dynamic data structures, where we want to be able to create items as we go along and glue them to other items. So what I'm going to do is each item will have a pointer that it can use to refer to another item somewhere in this collection. So I'm just going to create sort of a chain of these things where I create one and then create another one and glue the two of them together, and then create one more and glue that to the end of the ones that I've got so far. So each item will have a couple of data fields. So let's say I don't know, this is part of an inventory system maybe. So we've got these items that each have a name and a price. And so each one will also have a pointer to refer to another item. So I'm going to refer to these things as next and think of them as kind of chained together. So you'll have the first one, and then it'll have a pointer to the next one, and that can have a pointer to the next one, and that can have a pointer to the next one. And what we'll do is set these pointer field, the next field, to null if there is no more. If I'm the last one in the chain, then I'm going to set that to null. And otherwise, if there are still more after me, I'll have this point to whatever the next item is in the sequence. So we can now set up our structs so that individual items can refer to additional items in the collection. So they've got data fields plus a pointer to another item, and we'll just go through and use new and delete to dynamically create these things and get rid of them when we want to. So we can chain together as long a list as we like of these things, and what we'll do is just have, let's say, the main routine keep a pointer to the first one, whichever one is first in line, and then we can follow these chain of next pointers to get at the one after that, and the one after that, and the one after that, and so you get this kind of long list of things that are linked together, which is why these things are often referred to as linked lists, a list of items where each one has some kind of a connection to the next one in the chain. All right, so to set this up, we'll just kind of do this manually for the moment. Again, I'm going to use null to indicate that there's not an item. And so I'm going to set up a pointer to keep track of the front one. And initially, I'm going to set that to null, indicating that the list is empty right now. There are no items so far. So again, front is just a pointer to an item. And so we'll try and create the very first item. So I'll say front is equal to, and we'll create a new item. Again, this might not work, so I should check and make sure that it's not null afterwards. But if it worked, then I can go through and set the name field and the price field in that item. And again, I'm using that dash greater than notation to say, okay, well, through this pointer, get at this field. And then to indicate that there's nothing after it yet, I'll set its next field, the next field for that first item, to null. So this is the one and only item in the list at the moment. So then I'll go through and say, well, how about now let's create a new item, and I'm just going to glue it in at the front. So the newest thing that I add is actually going to be at the front, and the older things are going to be behind it in following this chain of next pointers. So I'm going to have a separate pointer. I don't want to wipe out my front because then I'll lose access to the one that I created a minute ago. So I'm going to create a pointer called temp, let's say, for the new item I'm creating. I'll use new to try and create it. And I'll make sure that that's not null, right? Make sure that new actually worked. And I'll do the same sort of idea where I read in the name and the price for that new item, right? Going through the temps fields. And what I'm going to do is to put temp at the beginning and front after it. I'll say temps next is front. So I've got this original item that I created and this new item, and there's a pointer from the new item to the original item, right? This temp next has a pointer to the front one. And then what I'll do is say, okay, well, now that that new item I created belongs in front now. So I'll set front equal to temp. So now my front pointer, my front variable, points at the one I created second, and inside that, it's got this next pointer that points to the original. So you can start gluing new things at the front. I can do this as often as I like, right? I can do this 20 times in a row where I keep going, create a new item. If it worked, fill in its fields, and then put it in front of whatever was the front item before. And glue in this chain, right, to make sure that I've always got a list to a connection to the things that I created earlier. So this is creating a sort of a list of everything in reverse order. The most recent item is in front, and then the thing that was created before it is next, and then the thing that was created before that is after that. And I can go through the chain when I want to, just processing it however I like. I can go through and print them, I can go through and search it. And if I want to go through and print them, then I'm going to have a kind of an extra variable, let's say current, that'll be a pointer to the one that I'm printing out right now. And I'm going to start at the front and I'm going to go to the back. So I'll say current is equal to the front, and print out a little list. Here comes the items in the list. And so while I still have an item to print, while my current isn't null, I'll print out the fields for current, the name and the price, and then I'll set it to point to whatever's next in the chain. So the item I'm looking at right now has got this next pointer in it that refers to whatever is further down the road. And so I'll just say, okay, well, replace current with whatever's next. And so I'll just walk my way down the chain, printing the name and price of each item that I see. And eventually, the last item in the list, which was the very first thing I entered, has got null as its next pointer. And so eventually I'll get to the point where current gets set to null. And I go, oh, I've reached the end, and I can stop. So I can go through one item at a time, printing out everything in that sequence. And I could do something similar, if I wanted to search the list for an item with a particular name or an item with a particular price, I could go through and say, okay, well, while current isn't null, if current's name is equal to the name I'm looking for, then, print out the name and the price. Right? So I can do anything I want with this list of items. And this is going to be a very common structure for what we try and do with these things. I can, it was fairly easy for us to stick a new item in the front. I'm going to do something kind of the reverse of that here, where I'm going to take the front item, chop it out, and get rid of it. And so what used to be behind it is going to be the new front item. So what we'll do is, again, create a pointer for the thing that I'm going to grab and chop out. And it's going to be the thing that's at the front of the list. So front is pointing to that first item. And as long as it's not null, right, I don't want to try and chop something out of an empty list. As long as it's not null, then I'll move front to point to the next thing in line, right, whatever was the second item. So I adjust front, and then this current item, the one that I'm chopping out, I'll stick its next field to null just in case, just to make sure that it no longer has any kind of a reference to the rest of the list. And then I can do anything I want with it. Maybe I print the one that I'm deleting, but then eventually I delete my current item, right? I delete the kind of the victim, the thing I want to chop out here. So my front pointer still has a valid pointer to what used to be second in line, and current has gone through and gotten rid of whatever was first in line. So again, I can glue things in, I can chop things out. Now, there are, you can get as fancy as you want with being able to, I want to insert at the back, or I want to be able to search through some point and insert in the middle. We'll play with a lot of that in the next course, in 161, where we do a lot of work with these kind of dynamic data structures, but you can see the basic logic that we're following through now. Now, we mentioned with the pointer bugs this notion of memory leaks. If we chop an item out and forget to delete it, we change that pointer, we had that current pointer, for instance, pointing to the thing that we wanted to get rid of. If I change current to something else, then I've lost the ability to access the item I want to delete. So do remember to delete the items when you chop them out of the list. Otherwise, the memory is unrecoverable, and eventually you get this kind of growing collection of things that you've chopped out but not deleted, and they're all sort of chewing up memory someplace that we no longer can use. And so that's basically just wasted memory until the program eventually ends. And again, you can wind up with a crash if you run out of memory while the program's running, so it is something that we want to be careful with. All right, so this idea of a dynamic data structure, things that we can create pieces and glue them in, or pull pieces out and delete them, is a very common idea. The approach that we took here, the sort of linked list approach, is probably the simplest form. Typically, we either set it up so we can just add things to the front or add things to the back. Maybe, in that last example, we just had a pointer to the front of the list. Maybe we actually keep pointers, 2 pointers, one to the front and one to the back, making it easy to access either end. Then there's all sorts of variations on that kind of idea. Queues, where we're always adding to the back and pulling from the front. Stacks are kind of like the example that we just did, where we're kind of adding to the top, the front, and removing from the front or top. And then we can come up with much more sophisticated data structures if we need to. So I'm just going to kind of run through a couple of examples here. So the idea of a queue, where you've got a bunch of items that are kind of connected together. We've got one of them in front, and when we want to remove something, we pull it from the front. When we want to add something, we glue it in the back. The stack, where we've got the original item, and then we add something new on top of that, and we add something new on top of that. So we're always adding new things at the top and removing things from the top. The idea of a tree, where we've got kind of one root item, and it's got a couple of children, and those items each have a couple of children, and so we get this kind of this tree, an upside down tree, if you like, where we've got the root of this beast, and it's growing downward, and each item can have multiple children, and we can go through and access what's down there. The idea of a graph, where we can have a whole bunch of different items, and any item can have connections to any other item. So we've got all sorts of much more complex structure to keep track of. But again, all sorts of different structures where we can insert a new item and insert the connections to the existing items, or remove an item by breaking the connections to the other items and then deleting the one that we're getting rid of, or processing and deleting the one we're getting rid of. So we'll focus on just the kind of linked list side for this semester, but again, next semester we'll get into a lot more interesting dynamic data structures. All right, I did want to play with just a little bit more linked list code to illustrate this. So this is essentially the same idea as we just did, only we'll use functions for this one. So I'm going to have a list of items. I'm going to call them contacts, where we've got a name and a username for each of the contacts we're keeping track of. And each of these things will have a pointer to the next thing in line. So we're going to follow the same basic idea, where we can add a bunch of items at the front, and we can print the list, and eventually we can go through and delete them all. So I'm going to have a function that creates a new contact. So this is going to go off and ask the user, what's the name, what's the username? We'll create a contact, and we'll return a pointer to it. Then we'll have an insert function, where we pass it the front of the list so far, and we pass it the new item that we want to insert, and it adds that new item at the front of the list. Now, since this insert function is going to have to change that front pointer, we'll pass that one by reference. And this one's going to return true if it worked and false if it didn't. And probably the only way this can break is if somebody passes us a null pointer to insert. So if somebody passes us a null contact to insert, we'll return false. Otherwise, we'll insert it, update front, and return true. A print function that just goes through from the front to the end, printing each item as it goes. And then a deallocate that goes through from the front to the back, getting rid of each item as it goes. So those will be the functions. And in our main routine, just to illustrate this, we'll set up a pointer to a front item, and we'll make it initially null, right? Our list is null at the beginning. So my front is a pointer to a contact, null at the beginning. And I'm just going to go through and create 4 items and insert each item at the front. So 4 times, I'm going to go through and call create con to create a new contact, give me back a pointer to it, and then I'll call insert on front and the new item. And as long as insert returns true, I'll assume that worked okay. If it returns false, then I'll print out an error message. So after those 4 items have been inserted, I'll go through and print it out. Oops, and then maybe we'll go through and deallocate once we're done. So let's go through and delete the items. And what did I call it? Deallocate. And we pass it our front pointer. So the main routine should be pretty straightforward. So we just have to think about what these things do individually. So for create a contact, again, we just want to create a new contact, make sure that it actually worked, right? It could potentially fail. As long as it worked, we'll get the name, put that in the name field, get the username, put it in the username field. We'll set its next field to null, indicating that as of yet, we don't know of anything after this, and we'll return it. And then the main routine can deal with inserting it or doing whatever it wants with it. That insert function was the one where we were saying, okay, you give me a pointer to the front of the list, pass it by reference so I can change it if I need to, and give me a pointer to the thing that you want to insert. So if the thing they want to insert is a null pointer, I'm just going to return false. And I'm not putting null pointers into my list. It doesn't work. Otherwise, if it's the very first item, if front is null so far, there's nothing in the list yet, then I can simply set front to be that new item. Right? Its next pointer is already set to null, so this effectively makes it the one and only thing in the list so far. Otherwise, it's one of the later calls and there's already something in front, so what I want to do is set my new contact's next field to be that old front item, and then say, okay, well now the new front is that new contact item. So set the new item's next field to front, and then front to the new item. So again, we kind of glue this new thing at the front and adjust front so that it knows that there's a new front item. And we return true to indicate that this worked. Right, so again, the insert isn't too bad. Printing it out, we just start at the front, and as long as we haven't hit a null, we keep printing the current item and then moving on to the next one. So if front is not null, I'll say, okay, well, here come the current contacts. If front is null, then I'll say, well, there's nothing in the list. And then I'll go through, right, start current at front, and while I still have an item to print, I'll print its name field and its username, and then I'll move it on to the next item in the list. So whichever item I'm on right now, say I want to move on to the one that's after that. And this will just go through. The last item in the list has got null in its next field, so eventually we'll wind up with a null in current, and this thing will stop. All right, and then finally, the one to go through and delete each thing one at a time. Again, we'll just start at the front, and as long as front's not null, as long as there's actually something there to delete, we'll have a pointer to keep track of the one I'm about to delete, and I'll move front along to point at the one after that. So front is now pointing at the next thing, and I can delete the one that I'm trying to get rid of. And again, this will just cycle through, right? Front is constantly moving on to the next and the next and the next and the next. Eventually, it'll hit that one whose next field is null, and this loop will stop. So hopefully, this will go through and recompile that beastie. And it should ask me for four, names and usernames. And I'm just entering kind of garbage here, but so it did actually go through and say, okay, well, here come my current contacts. And you'll notice that because I'm always putting the newest one in front of the others, when it prints it out, right, it prints out the newest one first, and then the one that was before that, and then the one before that, and then the one before that. But it's successfully going through and detecting the end of the list. So we can go through and develop these collections of functions and our struct definitions to build up something that grows and shrinks as time goes on. All right, I think that was everything that I wanted to go through for this for now. We will certainly come back and visit this kind of idea a fair bit in the future.